Hi class. In this video, we're continuing our discussion from section 4.2, where we were looking at second order linear equations with constant coefficients that look like a y double prime plus b y prime plus cy equals 0. And when we have one of these, we get our characteristic or auxiliary equation, which looks like ar squared plus br plus c equals 0. And we want to solve for r. And so there's three cases. One is that roots are real and distinct. So there's two distinct roots that are real. Two is that there is a repeated real root. And so both of those cases we covered in the last video. And so this video, we're going to cover the case where there are two complex roots. So that comes up when the discriminant is negative. So when b squared minus 4ac is negative, the roots are, now instead of calling it r, I'm going to call it z plus or minus r alpha plus or minus I beta. And alpha and beta just come from the quadratic formula. So alpha is negative b over 2a, and beta is square root of 4ac minus b squared over 2a. And you can and should work out the details of where those came from just by solving the quadratic formula and assuming that that quantity is negative. So, we want, or based on the last section, we would think like, are the solutions to our differential equation, e to the z plus or minus t. And the problem is that with that is that we want real solutions. So what we're going to do now is work out from this idea, what would real solution, how can we use that to try to find some real solutions? So now what we're going to do is a little bit of complex analysis to work out how to do this. So you may have seen this before, but if not, that's okay. But what you probably have seen is, I hope you've seen, is the Taylor or McLaren series, where if you can take the derivative of a function infinitely many times, then you can express it as the series of, like a power series with all of your derivatives. So in this case, we have our series is centered at 0. The Taylor series is centered at 0. McLaren series could be centered somewhere else. We'll mostly focus on the Taylor series here. So you just evaluate your function at that center point at 0. And then those are the constants, but then you get these powers of n over here. And then what makes it a power series, it's like an infinite polynomial. So this is a constant term, and then this is your x term, your x squared, blah, 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 xn, and it goes on for forever. Okay, so a couple examples, a couple of really simple examples of that are sine and cosine. So I'll write these out, and you can think about how you can like, kind of confirm that that makes sense to you. So for cosine, all of the odd terms drop out because um, when you take derivatives, the first derivative of cosine will be a sine, and when you plug in 0, it's 0. And so the derivatives, these coefficients, are going to flip back and forth between 1, 0, -1, 0, 1, 0, -1, 0, blah, blah, blah. And same with sine. So, so every other term is going to drop out, and you get only even terms with cosine and odd terms with sine, which is related to the fact that if you think back to just functional functions, cosine is an even function. You can flip it over the y-axis, and sine is an odd function. You can rotate it around the origin. Anyway, that's a different topic. Now, this Taylor and McLaren series can also be calculated for complex functions. So let's think about, let's do this in green, e to the I theta. So when we take derivatives of a complex function like this, we just treat I like a constant, and remembering that I squared equals -1, right? And so we take the derivative just the same way. And so when we plug in 0, e to the I 0 is 1. So first term is going to be 1. And our next term, by using chain rule, we end up getting an I in front of each derivative. And so we'll get an I, and then e to the I theta is just 1, and then we get theta as our variable. And then our next one, we get another I, and we get a theta squared. So we get 2 i's and a theta squared, so we'll just square both of them. And we get a 2 factorial, etc., etc., etc. Now, remember that, I cubed is going to be -I, and I to the 4th is +1. I to the 5th equals I, and so forth, right? So as we take all these terms and we know that I sort of rotates this way, and so we can simplify this a little bit to be 1 plus I theta minus, so now we get a minus theta squared over 2 factorial minus I theta cubed over 3 factorial plus theta to the 4th over 4 factorial, etc. Okay, and so if we group the terms that have I in them and then the ones without I, we get this. And we see that we've got exactly the same thing in each term we had before. We get a cosine theta. We can pull the I out of this one. So cosine theta plus I sine theta. Okay, so that gives us Euler's formula that e to the I theta equals cosine theta plus I sine theta. Okay, so that's really handy. That tells you how to break an exponential function basically into a real and an imaginary part. And so let's go back to the solutions that we found. We had our e to the z plus t and z minus t. So let's think about e to the z plus t, okay, which is equal to e to the alpha plus I beta. Remember, z plus is alpha plus I beta, and z minus is alpha minus I beta, and then a t there. So we can write this as e to the alpha t times e to the I beta t. And using Euler's formula, we get e to the alpha t, so that's kind of real. And then we get a cosine theta t plus I sine theta t. And then we could also write that as e to the alpha t cosine theta t plus I e to the alpha t sine theta t. So our complex function has this real part and an imaginary part. So we could use complex arithmetic, which I'm going to skip right now, but you can work it out yourself. You can show that our two complex solutions, e to the z plus t and e to the z minus t, are solutions to the differential equation that we had at the beginning. Okay, so that's great. We've got some solutions. It's wonderful, but what about real solutions? So for that, let's have a lemma. I'll write it up. So let's suppose we have a complex valued function z of t. And so what this means here, let me just scratch out a little bit of stuff about complex numbers over here. A complex number z equals alpha plus I beta, right? And so, this has a real part and an imaginary part, but these are both, like alpha and beta are both real numbers. And then the I beta is the complex part, or it's the imaginary part because it's got an I in it. So now similarly, every complex valued function, z of t, can be written in the same way. Some u of t plus I v of t. So for whatever, if z of t spits out alpha plus I beta, then u of t will spit out alpha and v of t will spit out beta. So that means that these two functions are real valued. Okay, so suppose we have some complex valued function that's got its real part u and its imaginary part v. And that is a complex valued solution to our homogeneous equation H. Then we're going to prove that both of those component parts, u and v, are also real valued solutions to H. Okay, and this is actually really simple. So let's see, because z of t is a solution to H, we can plug it in, which is going to give us a times y double prime. So when you take the derivative of this function, z, you can just do it component-wise. So you get u double prime plus I v double prime plus by, b, and now we're going to plug in u prime plus I v prime plus c u plus I v equals 0. And we can just shuffle these things around and we get a u double prime plus b u prime plus c u plus I a v double prime plus b v prime plus c v equals 0. And just like with complex numbers, if alpha plus if alpha plus I beta equals 0, that happens if and only if alpha equals 0 and beta equals 0. Okay, because in the complex plane, 0 is equal to, 0 plus I 0. That's the only way that you can express 0 is by having both the real and the imaginary part to be 0. So it's the same thing with functions. So um, this thing happens if and only if um, each of those terms in parentheses are equal to 0. So, oops. So this is if and only if both of those expressions are 0. And of course, that's the same thing as saying that U and V are solutions to H. So that's just what we wanted. Um, so there we go. So the point of this here is that if we are given a complex solution, which we had, because remember we found some complex solutions up here, that means that we can also find some real valued solutions. In particular, these guys right here. So if our e to the z plus t and e to the z minus t are 0, then we can find these real valued solutions. And let me write that out this way. So if you have the situation where the characteristic equation to our homogeneous equation H, if that characteristic equation has two complex conjugate roots, a plus or minus bi, then the way that we find our two linearly independent solutions is given by these formulas, either the alpha t cosine beta t and either the alpha t sine beta t, where you get the alpha and the beta from the roots of the characteristic equation. And then therefore, now that you have your two linearly independent solutions, you get a general solution given by this formula, where it's the familiar C1 times your first function plus C2 times the second function. Now, if you have your initial conditions, then you can use those conditions to solve for C1 and C2, just like we did in the last section. So now that covers all of the cases for our characteristic equation, whether we're going to have real roots, double roots, or complex roots. And those are all the cases that we're going to get. So now we know how to solve every homogeneous second order differential equation with constant coefficients. There we go. That is the case that we've covered. Whoops.